And this is, this is what you have to remember from this paper, that basically you can use masking to ensure autoregressivity in complex inputs, like spatial inputs. And this is in a way what they're also doing with PixelCNN and PixelRNN. Right. So this is more, let's say, right, I have a picture like that. So this is the ordering of your D visible dimensions, and these are your K neurons that you've got, your hidden feature that you've got. So your ordering is from 1 to K minus 1. What was it? Okay, I'll check this again. I'll open the paper and make a precise explanation after the break. But more or less, the idea is what I said. Like with the masking, you create these roots that don't depend on future values. And this is what was also used by modern autoregressive models. So we first decompose the data likelihood of an image by base rule. Here we've got n squared, because we've got n squared pixels. Each pixel is conditional. Each pixel conditional corresponds to triplet colors, right? Each pixel has RGB values. So we can be autoregressive not only in the number of pixels, but also in the channels that each pixel has. And more specifically, here they take it to the extreme. So they say that to generate the first red pixel of my IF, to generate the red channel of my IF pixel, I have to depend on all previous pixels before this, before IF. Then to generate the green channel of my IF pixel, I have to depend on all previous pixels, as well as my red channel for this pixel. And to generate the blue channel pixel value, I have to depend on all previous pixels, as well as my red and green channel for this pixel. So they take really like they decompose every dimension. That's choice, right? Like they could have also grouped things together, but they chose to do that. And they model conditionals with a convolutional recurrent neural network, because the NAID architecture is not easy to scale up. You cannot easily have very large inputs, very large images. Since this paper was specifically for images, you've got 256 values for each color channel. So the output is categorical. They say it's categorical, so they use a softmax to pick one of the values in the outputs. So it's a 256 softmax. Clear? Now, because it's convolutional LSTM, they have to make sure that their convolutions, especially when stacking one another, and you've got the effective receptive field that basically captures more and more input dimensions. Like that's the main problem, right? Like when you start stacking layers in a neural network, your second or your third layer might have like a receptive field of 3 by 3, but the effective receptive field, so the number of pixels that affect this ith neuron for your kth layer is much larger, right? Like the receptive field is much larger. So you have to make sure that, therefore, that whatever computations you're making, if you're caring about autoregressive modeling, whatever computations you make do not depend on future values. So they use a causal triangular receptive field like that. And they show that basically with this trick, you can ensure that you don't violate the autoregressive nature. You don't. So this is called the causal convolution. Right. The convolution only depends on the past I minus 1 pixel, not future ones. However, you lose some context, right? Because here for every pixel value I, you only care about this triangular shape. Any operation that makes sure you don't have access to forward pixels, whatever forward. Forward means here like you assume an order, like the snake-like order. For as long as you don't violate this order, you're good. They assume the snake-like order, and then they propose this triangular receptive field for the convolution effectively. It makes sense as far as autoregressivity goes, but from the data perspective, you're losing context because this pixel value does not depend only on those like triangular shaped receptive fields, but they have they much more depend on than other neighboring pixels. Yes?
How can I see this from text point of view?
Text.
Yeah, as now we have images all the time.
Right. So for text, I don't think you've got a problem because you don't have that problem because text is 1D, not 2D, right?
Yeah, I mean, okay. So then, but this so can you then still use this triangulation trick to? Then you just don't use convolution at all.
Well, I mean, you have to then reshape your text, so that would be a bit strange because the text you don't really need that. Here, the thing is that they want to use convolutional LSTMs. They could also use LSTM like that, but then they would assume really like a snake-like order, even for the way of computing the features. So you're basically saying that your image is not really an image anymore; it's literally like a sentence, a flat sentence of 256 values at a time. Yes?
Yeah, I was going to say, if they use CNNs, couldn't they take the whole image at the same time, but then like, I don't think you have like the causality.
One more time, sorry?
I'm saying like, if you pass an image, couldn't they just use like, why do they need to do this propagation? Couldn't they just take in the whole image?
No, because, well, not with an autoregressive model, because if you take the whole image, then future pixels, like you wouldn't have this independence between pixels. So future pixel would influence the computations of previous pixels. So your autoregressivity would be violated. You want to make sure that this is absolutely correct when you're using an autoregressive model to compute lighting. If your conditioning variables here have even a slight hidden dependency on, if your conditioning variables somehow influence your current value explicitly, or you have future values here in the conditioning variable, then basically the model can cheat, right? You just need to copy the future values. You don't have to model the future. You just copy the input that you already given.
Yeah. Do they use a mask in too?
Well, basically you can see this as a mask, like the way that the way that they model the operation is basically like masking the inputs. Like they have this particular shape, basically because they have the 12-layer convolutional RNN. So it's an RNN, so each layer it's modeled by an RNN with convolutions, and they want to make sure that these convolutions for the I pixel get information only from pixels from like smaller than I like order. Okay, it's clear. So this is raw LSTM, and then they propose the diagonal by LSTM, which is like another variant of such causal convolutions in the LSTM like conditional, and this is a bit better because it captures it doesn't ignore this lost context. So it captures a better context in an efficient way. And this diagonal by LSTM is basically a combination of two diagonals.
Why did they even start with the row LSTM? Because it seems more intuitive to just do the whole snake until the.
Because they have used convolutions. And convolutions, we know, are good feature extractors from deep learning. Like from convolutional neural networks, we know that they are very good when it comes to learning features for images. They could do the snake thing only, so then you would have really a sequential interpretation of an image, but then you're completely losing spatial context. You got an image here. Or at least what they care is about modeling images. For modeling images, using operations that take spatial context into account is important, like convolutions. Convolutions work really well. Now the question is, how can you use convolutions in an autoregressive model? It's not straightforward because a convolution, say that's your convolution here, a 3x3 convolution, centered around the pixel of like focus here. This requires access to these guys as well, like to everything around it, right? Like, so this cannot by default allow for autoregressivity, because if you want to model this with a convolution, you're also going to use future pixels, pixels that are down your snake-like ordering. A simple way is to just assume that you've got no spatial context, no convolutions, just MLPs, but then you're losing, you know, here. You're losing scalability and flexibility. With MLP, you cannot easily scale to very large images, then your models become very, very large, and also you don't capture any natural image statistics. You just assume that your image is simply a very long sentence of values. So you don't have an operation that can easily model the natural statistics in your data. It's what I said earlier. So you have a model which in theory computes your tractable density, P of x. So it is technically correct. However, not all models are equal, even in that like category. Some models will have a better way of approximating the conditionals. And for images, a natural, intuitive way of doing better conditionals is making sure that you take spatial context into account. And an easy way, or a well-known way of doing that, is convolutions. However, convolutions conflict with the autoregressive nature of the model. So how do we make them, how can we get convolutions that still capture context without violating the autoregressive nature of the model? Well, by diagonal row LSTM and row LSTM. Okay? So we could use a regular LSTM, but it would require sequential pixel-wise computations, one pixel at a time, less parallelization, slower training, and we would not take context into account. With row LSTM and diagonal by LSTM, we process one row at a time and we can do parallelization. And once you're in this regime, and for as long as you make sure that your basic convolutional blocks do not violate the autoregressive nature of your model, you can do whatever you want. So you can add residual connections to speed up learning. Again, it's a tractable density. It computes exactly the likelihood, which means that you can have nice image generation for as long as you can train it well enough. However, the training is slow because it is sequential, because you have to use LSTMs to model each conditional. Is this clear? And yeah, generations are quite good at the time. By now, of course, we've got much better. It's interesting, right? 3 years ago, that was good. Or 4, like it was very good, yes. PixelCNN goes one step further. You replace LSTMs with fully convolutional networks, so not even considering very far away pixels. 15 layers, no pooling layers to preserve spatial resolution. You use mask, again, like with MADE, to mask out future pixels in convolutions. And because we use now convolutions and not LSTMs, LSTMs are slow because you have to do everything sequential. Here is just a convolution. You just run a convolution operation on your layers, only with spatial types of convolutions. So you have better parallelization, like much more efficient. Pixel generation is still sequential and thus slow. Will this do a better way, a better modeling of your conditions and your likelihoods? What do you think? Well, we can give it a shot, right? Just yes?
No.
No, right? Because even in the previous case, we were using convolution, so you were taking spatial context into account, but you were taking much more, so you could take everything into account. So here, we're actually losing context. We sacrifice context for the sake of efficiency. If we assume we have enough computer to train the PixelRNN, that's already quite good. But PixelCNN is faster, so it generates a bit worse quality generations, but is faster. Yes?
Are these methods only used for like in-painting? That's what I saw on the last slide, I guess. Or part of it's included and then...
Here. Yeah, well, I mean...
Or are they also actually used for like... Because for like...
No, you can generate, right? It's like, these are generative models, so you can either condition and then generate autoregressively.
But yeah, that's what I was asking. Can these models actually do that? Because when I look at the in-painted part, it's already quite poor. I would say in this result. I mean, 3 years ago again, good, but already half the picture is there. So could it actually like generate anything that looked coherent? I guess my
It's
question.
coherent enough. Like back then, of course, as you said, like that's was the best possible. These were quite good, quite impressive results for color images. But yeah, like as you say, they're no match for what we have now. The progress is like really amazing. But this is literally like what was the state of the art 6 years ago, 5 years ago. Yeah. No, that's it. It doesn't matter the completion, especially for autoregressive models. You should think that completion is literally as if you start halfway in your base computation, right? So if you have p of x, p of x1, p of x2 given x1, p of x 100, x more than 100. Completion means that you simply, instead of generating these pixels, x1, x2, x3, blah, blah, you just take them from your observation.
Yeah, I got that. But I was just wondering, like, when you start to slide with only the first pixel saying, for example, it's blue or something, and it will start, you'll let it generate something, and you want the 100-bound image, I would assume you, with this method, when I look at, already when you have the first half of them, the whole image is quite poor, that if you start with, like, only the first one, you would get nothing.
Well, I mean, it's not like that far. That's quite good, I would say. I mean, I don't even understand what this image is supposed to show.
Yeah.
I guess it's a boat. But, well, I honestly don't know. But like,
looking
okay.
at the bottom part.
Right.
But you do get coherent images when starting just with a few.
Yes, you take coherent.
That was
I mean,
the
okay,
question,
yes.
yeah, sorry. Yeah. So good.
So that is, was that the question?
That was the question with yes.
If you take coherent pictures, if you start with a few,
Yeah, like does
do
it
you get
cover
something
the same,
coherent if
like
you
could it generate, for example, the middle picture only starting with a few pixels, like a few pixels. Or
If
something
you
like
check,
that. I don't know.
I think there are. Do I have some examples here? Let me see.
Because this doesn't feel like true.
Yeah, right. Like okay. So basically, you're asking about the generation. Like this is generation. So I don't know if this is coherent enough or not. And these were also cherry-picked examples, I suppose. I guess that this is like some sort of coral reef in a high magnification here, so that it's pixelated. It's I guess 64 by 64 normally, right? Yeah, it doesn't look terrible. You can understand that more or less that this is something underwater. But if it's like good enough, I mean, obviously it's not much to what we have now with diffusion models, but it's a remarkable success given what was before.
But that's what I also like. This was my question. You can generate something.
Yeah, you can.
Because I feel like in painting is sure it's like sort of generation, but it's like you're taking so much information into account it doesn't feel the same as starting with nothing, basically.
Right, but from a pure modeling perspective, it's
Mathematical
like
similar.
it's the same. Like it's just that you're having generation with like half your inputs already given, so you know for sure that they're correct. That's not really like cheating.
Can I ask?
Yeah.
So you would actually add another conditional like on the text or on the class that should be generated to when doing the snake?
You
Would
would like a
have,
conditioning? Sorry, come again?
yeah, another conditioning term like the text that should be representative of what should be generated, or how would you guide it to generate a coral reef from a blue pixel and not?
There is no such. I mean, so autoregressive models don't have latent variables. Latent variables are supposed to be those variables that model like context or global content. So here it's really like you sample. It's just like ChatGPT now. You don't really know what's. So actually, that's interesting. ChatGPT is an autoregressive model, as far as I know, like at least in the basic version, right? Why does it produce coherent answers? That's actually a fantastic question. Because it is trained in an autoregressive way, right? Like it's trained literally to predict the next word. Of course, there you're conditioning on the question, right? So you've got another type of conditioning. Here, perhaps you can have a conditioning on the types of semantics if you add additional information.
Maybe just literally the word that should. Like, if there are a limited number of classes that
Right.
are already in the training data set, could you condition it on that?
Yes, I mean you can have a supervised, so you can have an additional variable y that is your semantic class, and then condition on that. So have some sort of semi-supervised learning, and then generate images that are specific for a particular semantic class, right? Like you can, but this is not what they do here. I think I don't remember if they also did a semi-supervised setting, but yeah, I mean that's possible. You just have one extra variable to put in your conditional. So you're not going to condition only on your pixels, but also on your semantic label. Okay. Yeah, maybe this is what they did here, because otherwise it's very coherent, or I don't know. I don't remember. Yeah, so these are horses, sandbars. Well, anyways, it's supposed to be good. It was good at the time. It was quite good, and it's as you saw. Like, what is important here is like try to disengage yourself from the precise quality of the pictures, because this can be better or worse or whatever. You can also see it in the relative progress, right? And made were done using endless digits or not even. And the basic model was very similar to what PixelRNN and PixelCNN does. It's still an autoregressive model like using neural network. It's just that for PixelCNN and PixelRNN, you'd use a better neural network that uses better convolutions or better width, but the basic principles, the building blocks, are similar. So, you know, maybe the next type of generative model that will meet diffusions will be autoregressive, if you can solve problems of speed, efficiency. I don't think so. I guess it's like by now diffusions seem to be very good at that, but you know, who knows? I think they're still not like doing tractable density per se.
I thought that with like audio generation models, autoregressive models are still used quite a lot, even though diffusion also works very well.
Yes, I mean,
Right.
but because there
Because it's so sequential.
it is sequential, like that's the thing, right? So the thing is that for images, they're not per se sequential. I mean, you can call it sequential if you want. It's not wrong per se, but that's not necessarily the most natural way of understanding an image, right? You can also think of it like that. If you compress the image, you basically have the same content, right? Like even if you mask out random pixels, you more or less get exactly the same semantic information. So visually, there is something very special about our understanding, at least, of the visual signal. We don't require an autoregressive, and diffusion models exploit this very well because they use units. They really heavily rely on the unit inductive biases with whatever denoising operations it does. And we'll see. Diffusion models are basically, again, so that's the one thing. One moment. That's the important thing to realize here. That like all these generative models, they really try to solve the same problem. There's always an integral somewhere. First, you have to make sure that your integral is somehow computable, one way or the other, either by approximation, like in the latent variable models, or by taking some, like, making use of a loophole, like a Bayes rule here, right? That's the main first problem. This gives you a family of generative models, and then you have to make sure that all your operations are as efficient as possible and as close to your data, to the native nature of your data as possible. Okay, yes?
Yeah, I was wondering for like pictures, it seems very silly to do it indeed pixel by pixel. I mean, not silly, but maybe a little bit like counterintuitive what you normally see. Of course, most computer vision is dividing stuff in batches. Like, is there also like an approach which like basically learns like on top of like you basically go batch per batch, and then you learn besides you learn is basically like latent on a batch, then you take that as an input to the next batch, and you basically decode that latent, and then you basically go like.
Yeah, I think PixelVE does something like that. There are like there were some intermediate models that they try to combine latent variable models, like PixelRNN, PixelCNN. There have been such approaches. I don't remember exactly what they were doing. I think that. So like these are like you have to really go into the details of the papers, try to see a bit like even the like when I'm reading the raw LSTM paper here, the PixelCNN, PixelRNN, like this. I mean, it's very easy to understand what is really happening, like what is happening in the end. But how they come up is a bit like arcane. You have to like go check the computation. They also don't really explain it very well. But that's the basic idea. And for PixelVE, you have to again go check the paper, but they are literally trying to combine PixelCNNs with a latent variable model and make sure that you've got some good hidden representation, but not on the patch. I'm not sure if it's on patch level. I think it was more like the latent code is on the global level.
Okay.
Look, for as long as you pick your family of models, you have to compute your generation. You have to compute one way or the other, either this quantity or a let's say reasonable approximation of it. For as long as you do it in a systematic way, make sure that your individual computations are not theoretically wrong, and your individual operations are scalable, tractable, and so forth. Then you got a valid model that you can try. So yeah, how you put your intuition about the touch-based parsing, you know, like if you think about it, then you can translate it into a model that is autoregressive or latent variable. That's good enough. I'm not sure if, I guess people have tried all these variants. If not, you're more than welcome to think about it. So PixelCNN allows for faster training, and performance is worse than PixelRNN a bit because you discard context. You also have the blind spot here with PixelCNNs. but not latent space, as you said. These are the cons. There was PixelCNN++ afterward that improves on top of PixelCNN by doing a bit better modeling choices of neural network. So you're modeling the output by logistic mixture likelihood instead of a categorical distribution. The intuition there is that not all values in channel, in color channel, you've got these 256 values, but they're not necessarily best described by categorical distribution. Like if you take the histogram of values, they are not like uniform. In the categorical distribution, more or less you expect uniform or something like that. Well, if you have a better way of, like say some values are more preferred, like gray values are more often appearing, then having a different output makes sense. Also, softmax requires too many parameters and yields very sparse gradients. Very sparse gradients because not all pixel values are visited equally. Like you've got to have only one, so one gradient per category in the end. It conditions on whole pixels, not colors, so you don't take the R and the G and the B separately, but both, like all RGB, like all the pixels. And then they also do some architectural innovations. In general, you got really good density estimation with autoregressive models. Like it's literally doing that, right? Like it's the definition, let's say. And then they can take into account complex codependencies, right? Because all the conditionals can capture that. So for example, if you have perfect modeling of the conditionals, then you got like all the dependencies your data is there. They are not necessarily latent variable models, so in their pure case, unless you have the semantic label, some other additional variable that corresponds to semantic labels, you're not going to have controllable generation like that. They don't have an encoder per se. They're also slow in learning, inference, and generation because computations are sequential, and you might have artificial bias because of the order you assume in your data if it is not a natural order. And let's have a quick break, 10 minutes, and continue with normalizing flows. And let me check the mate paper now.